Okay, we've looked at vectors graphically, we've defined what they are, and we've talked about how to add vectors graphically, and we've discussed their components. In this next set of video lectures, we're going to talk about how to do vector addition by components. And we're going to start off adding vectors that are already at right angles. Because two vectors at right angles will give us a triangle, a right triangle, and we can then pull in some trigonometry and a little bit of Pythagorean theorem. So our objective here, we want to add vectors at right angles. Okay, let's talk about what we know coming into this that's going to be useful. We know this key thing about these two things, about right triangles. Given a right triangle, the tangent of the angle, the acute angle, is equal to the opposite leg length divided by the adjacent leg length. And this leads us to the idea that we can solve for theta, the angle, by taking the inverse tangent of both sides. And so theta is equal to the inverse tangent of the opposite leg length divided by the adjacent leg length. We saw that previously. And we also know the Pythagorean theorem, again given a right triangle. The Pythagorean theorem says that the leg squared plus the leg squared equals the hypotenuse squared. And we can take the square root of both sides to come up with the fact the hypotenuse is equal to, and we're just focused on the positive because we're talking about geometric figures, the square root of the leg squared plus the second leg squared. Okay, so those are things we know coming into this, so we're going to use those two things. Okay, having developed the meaning of having developed the meaning of components. Okay, let's recall, when I use the word components, we're thinking, for our purposes, that we're talking about the x components and the y components. The x component, the horizontal component, the y component, the vertical component. And we can now add vectors to any degree of accuracy that's required. Graphically, we were stuck. We got a pretty good idea with our protractor and our ruler, but we couldn't get, it was all based upon how precise we were being measuring things. Using components, we can get very precise with the resultant vector, the sum of the two or three vectors we're talking about. How do we do that? All right, given two vectors at right angles, again, we're going to just discuss right angles in this video lecture, we can add these vectors using, one, the Pythagorean theorem, which will find the magnitude, r, not bold-faced, not with an arrow above it, of the resultant vector r. So how long, what is the size of the resultant vector? And we can use the inverse trig function. So I'll come back up here, make sure we can see it. So we're going to use this, the Pythagorean theorem, to find the magnitude of the resultant vector. And we're going to use the inverse tangent function right here to find the direction of the resultant vector, specifying its direction as the standard position angle, theta. And of course, standard position means we started on the positive x-axis and we rotated around from there. Okay, that's the standard position angle. Okay, I'll do one example because I think this is going to be pretty self-explanatory, or pretty simple to think about, given they're already at a right angle. Add vectors A and B. A has a magnitude of 14.5. B's magnitude is 9.1. The vectors are at right angles. Okay. So here is vector A, and we know that its magnitude, A, is equal to 14.5. They're at right angles, so I'll draw B here. This is vector B, and we know that B's magnitude is 9.1. We're going to add them, and so we're going to come up with this vector, and this vector is the vector R. And of course, there's our angle theta. Okay, we want to come up with what is the magnitude and what is the direction of our resultant vector r. Okay, so let's see here. Magnitude. We're going to use the Pythagorean Theorem. Okay, so the magnitude r is equal to the square root of leg squared plus leg squared. Well, this leg has a length of a, its magnitude is a. I'm going to write a squared, and this leg, vector b, has a magnitude of light typeface b, and so I'll write it this way. This is leg squared plus leg squared, the magnitudes, which means that r, vector r's magnitude is the square root. Well, a is 14.5. and we'll square that, and b is 9.1, and we'll square that. And so the magnitude of our resultant vector is, I'll just pop that into a calculator, and you should come up with 17.1 units. Okay, let's now find the direction. What is theta? So I'll go here to direction. Okay, well, we're gonna now we're back up here. Use the inverse tangent function to find the direction. Okay, the theta is equal to the inverse tangent, and of course we know it's opposite over adjacent. Well, the opposite is b, the adjacent is a, so it's the opposite over adjacent, which is the magnitude of b over the magnitude of a. Okay, let's continue on. Therefore, theta is equal to the inverse tangent. Well, the magnitude of vector b is 9.1. The magnitude of vector a is 14.5. And we're going to pop this into our calculator. Make sure you're in degree mode, of course. And you're going to come out with a standard position angle of 32.1 degrees. So this angle here would be 32.1 degree angle. So add them up. Our resultant vector is r with an arrow above it indicate vector. Okay, r is the sum, so we added them. The resultant vector is the sum. The result is a vector of magnitude of size, but r equals 17.1. Again, without an arrow above it, it indicates magnitude. And it is directed at a standard position angle, of 32.1 degrees. Again, we're starting on the x-axis. We're going counterclockwise from the positive x-axis, and this angle right here, from this point, here to here, is 32.1 degrees. Okay, so that's adding vectors that are at right angles. From a vector addition standpoint, that's about as simple as it gets. I want to make one note here because we're going to make use of this. Note, okay, the tangent, the inverse tangent of the opposite over the adjacent. Okay, I'm going to come back up here and talk about, we are right here. That's what we were using, the inverse tangent of the opposite of the adjacent. We discovered here, okay, is equal to the inverse tangent of the y length over the x length. Okay, we have that right here. The y length and the y direction was the magnitude of vector b. This is the y length, and the x length right here was the magnitude of vector a, 14.5. So this is going to come in to play as we go into future, and probably the next video lecture. But we want to keep that in mind that we're going to be playing with this, the y length over the x length of the components.